the last class, we have been discussing about the membranes, the membrane, the microfiltration membranes, and we discussed about how microfiltration membranes they work, and what happens when how we can kind of tell about the ratings of the membranes and how do they actually take part in. So we can calculate what is the log rate and log values of the membrane. So these are the ratings of the membranes in terms of the pore sizes or molecular weight and also the performance. Now, as we have said, that membranes are basically, it is the stuff that restricts the flow across the membrane. And deal with this, the restriction of flow actually causes a lot of pressure differential in the membrane. So and that causes a lot of problem that is known as fouling. So let us first discuss about how we can define. As you have seen that for normal, we have gone through because what we discussed about the rapid sand. So for rapid sand, for rapid filters, we had derived a formula for and we also said that net loss is we found out the formulas for it. But if you can recall that there was a term the length of which is what is the hydraulic gradient or net loss. You can imagine or consider that our filter is just a small portion of our membranes. Our microfiltration membranes are they are just a smaller portion of the sand filter that we are having. So then with this we can actually can draw a membrane vector. So suppose this is your membrane, and so definitely the filter, the net loss across the membrane should have a length component. So length is what? So this is, in this case, we can call it small l, or we can call it, let us call it small. And also we had the value of determining, determining the passage of water. So here also we have this, and then this is, but this is just the mu is nothing but mu is nothing but now here there is a fundamental difference is that here we talk about the volume of the membrane, but here we do not really talk about the volume of the membrane. So what is important to us is the area of the membrane. We can have this membrane at different configurations. Suppose we can have it like
चल हाँ हाँ लिखे जाए
so all this surface.
12 बजे का
So
टाइम
this
11
all
से
this
12, 10
surface
से 12।
acts like a
नहीं
membrane.
ये तो होती तो टाइम नहीं लगता है चल
Configuration.
एक काम
तुम्हारा तुम्हारा कट हो जाएगा क्या
So we
जो सी बात
that
कर
is
सकते
why
मैं कहता नहीं जावा
यहाँ पर जान
the
दोनों दे जाते हैं जितने लोग लाते हैं क्या
no, the area of
तुम्हें कब लगी
30 सितंबर
कहाँ कहाँ
किस तरह समुद्र पास है
wise
आपके
we
लगे 29 सितंबर।
अरे एक है हम 30 का
looking
दिन
at
चलो लोग आया
the flux of the membrane. So we are not talking about the discharge or Q. We will be talking
एक दिन
about
लोग आया
the flux of the
29 का लगा हुआ जी।
So how the flux of the what is the flux? What is flux? Flux is nothing but equals to
सोमवार है तुम
the if you consider okay, so this is an area through which your flow is taking place. Now it doesn't have only some area but no depth. So in this case, how we define the loading on this membrane? So it is defined as the flux of the membrane. It is nothing but the discharge or the flow rate per unit area of the membrane. So this is how the flux is defined, and when there is a flux or passage of water in this membrane, then obviously, as we have seen in the filter, there will be a head loss, and if you have a pressure of P1 here and a pressure of P2 here, so then your pressure drop or the head loss across the membrane is P1 minus P2. Okay, so this is that we call it a transmembrane pressure. So this is known as transmembrane pressure. Okay, and this is, and flux is always written as J. Okay, so in place of so this is the flux J, and this is how we write the flux value. So in other words, flux, if you look at the dimension, this is let's say meter per hour, and this is meter square. So it has got a unit of meter per hour, which is the unit of velocity. And if you can understand, when we talked about flow through a porous media, we always look at what is known as Darcy's law, right? And what does Darcy's law say? That velocity through a porous media is proportional to the hydraulic gradient, or in other words, we can write coefficient of permeability into I, where I is the hydraulic gradient, where we can define I as hydraulic gradient. Okay, and coefficient Kp is hydraulic permeability coefficient. Okay, and then let us write delta. So here, so what is the value of I here? Let us say that our Darcy's law is valid here also. So this V is nothing but equals to our J. So we can write J equals to K. So G equals to Q by A equals to let us write this Kp. Okay, Kp, and what is delta P here? Delta P is again, as we say here, delta P is nothing but equals to rho W G into HL. So as you know from this is the head loss here. So we can write I equals to HL by L, Okay, and the head loss is given by this. So with this we can write this as uh, delta P divided by uh, rho G L. Okay, because we are talking about over this length L, and this is how we can write this. Okay, so now you can see that delta P for so Kp is the property of the membrane or coefficient of hydraulic permeability, and Pw, rho w, and G, they are specific. G is a specific, G has this constant value, and rho w, if we say rho w for water, this is rho w for other substances. You can have different rho value here. So in other words, you can write this as rho wg divided by kp, and you have this as L. Okay, and then we can write it as J equals to delta P into okay, and for a particular membrane, here, so what we can also write that we can include this. And there is another thing which I want to say is that viscosity has a role to play. So we, with this analogy, we can write this as delta P mu by Km. So where all these components, rho W, G, L, and part of Kp, it is kind of incorporated into this Km value. So in other words, we can write, this equation as delta P divided by mu and Km. So mu is the viscosity of water, which you can see this is the same as the more dominant formula here, J equals to delta P into porosity 32 mu by L into d square, where the pore size is d square and all these things are incorporated. So this is our equation for the membrane. So Km is called membrane constant, or and this varies for membrane to membrane and also on the thickness of the membrane, and then, or sometimes we call it as membrane resistance coefficient. Okay, and so you can understand. So this is the delta P mu by Km, and if you want to, if you see here, mu by Km is like for a particular medium, mu by Km is nothing but a constant. So for a particular membrane, if I want to increase the value of J, then we have to have increase the value of delta P. So there is a linear relationship between J and delta P, and as you can understand that we have to increase the value of J, so that we can have higher value of delta. Increase the value. In order to increase the value of J, we need to have a higher value of delta. Now, so this linear relationship suggests that if we want to mainly maximize the flux, so for any particular membrane, we'll be happy to maximize the flux. But if we try to do this, then there is something that comes in, in between, is that this relationship is good for, this is good for water without any particle, or let us say deionized water. So it is good for deionized water, or maybe it is good for uh, uh, you know I mean uh, water with any contamination or any suspended particle. But if we have a suspended particle, then can we withstand very high pressure of operation? So suppose you have a very high pressure across the membrane. So there are things that will happen is that sometimes when we do this, then there will be something called fouling. Okay, let me show you a diagram about fouling. Then you will be understanding. Mm, I have a diagram from ultrafiltration membrane. So if you have a look at the diagram, see this is a cross section of an ultrafiltration membrane. Okay, and as you can see that as if we do a cross flow situation, so these shaded lines are the surfaces of the membrane. You can see this porousness of the membrane here. The shaded line is basically the surface of the membrane, and if the particles are kind of get trapped right here. Now if you increase the pressure around this area, so what is going to happen? Some of those particles will be pressurized to move inside the internal of the membrane. Now if it moves into the internal of the membrane, we have a big problem, because later on you cannot remove them. Now how do you remove all those surface fouling or surface deposition? So these depositions are called fouling of the membrane. Okay, and the fouling of the membrane is basically different types. I will discuss that. But if you increase the pressure, some of those particles will be forced to go inside this membrane. So so they will be like stuck inside the membrane forever. Normally we do backwashing, just like the filters, to get rid of these particles here. So we can get rid of these particles just doing backwashing. So if you reverse the flow rate, then these particles will get dislodged and will come out. Now if the particles are getting inside the tortuous nature of the pores inside the membrane, they cannot come out. Suppose for this particle it will be stuck here. If you try to do a lot of forcing, using high pressure backwashing, still this particle may not be able to get out of this membrane, because whatever force that you give, it will be stuck here. So there is a limit to which we can clean the membrane using our conventional backwashing method. So this is called like internal membrane fouling, and sometimes or many of the times they are irreversible, so we cannot really reverse them. So what happens is that we cannot, if we want to make our pressure very high, so that we can have very high degree of flux or through the membrane, it is not possible, because that will increase our fouling. So we have to strike a balance between the flux and the fouling of the membrane. Okay, so this is one of these problems that we face when we have like high TDS water, so that over time the fouling of the membrane will take place, and then of course there will be problem associated with it. Now let me show you a figure of a fouled membrane. So let us say this is so look at the first figure here. So this is a fouled membrane. So you can see that all the particles. So this is a TCM diagram of a fouled membrane. So this is an ACM diagram of a fouled membrane. Uh, so here you can see all these particles are, you know, they are on the top of the membrane. Now, if you do a back pulse or backwashing, then fine, some of the particles will get dislodged. Normally if you have a back flux of 0.1 second, then this is the scenario. Now you can do a back pulse of 1 second, then you can see this is the scenario. At the bottom, you can see the membrane, the pores of the membranes at the bottom. And then if you do the back pulse for 180 seconds, of course it is cleaner, but there are still particles that you can see on top of the membrane, and also in below, in the depth of the membrane, there might be other particles too. So back pulsing for a more duration of time will be required for considerable cleaning of the membrane. But even after that, there will be particles which will be there. So there is something called irreversible fouling that will be there. Okay, and so in order to get rid of those irreversible fouling, so what happens? Before I discuss this, let me discuss this one. So if you put this membrane into service, so you will not get the same pressure drop as you have calculated for a clean water. So whatever the formula that we have written here, this is for a clean membrane. But as you can understand that a fouled membrane will have a high pressure drop, right? So as you do your treatment, then the transmembrane pressure for the same flux, the transmembrane pressure is going to increase over time, right? So if that increases over time, then you understand that when you reach a kind of a limiting value of transmembrane pressure beyond which you cannot actually increase the pressure because the membrane can get damaged, so you decide to give a back pulse. Okay? So when you back pulse the membrane, the membrane is clean, but not to the extent that is similar to a clean membrane. So when you start this operation again, so you see that you are starting, your so-called clean membrane has, greater amount of pressure drop, than the clean membrane. So as you go on doing cycles after cycles, then obviously your pressure drop across the membrane or cleaning membrane will increase. So please look at this diagram now. So this is a history of microfiltration membrane over time. So you can see these ripples right here. So this is the start of this is a clean membrane, okay, or the new virgin membrane, this is here. Okay, now you decide, you run this, and then you have the pressure drop increasing, and then you stop here. Okay, and at this point of time you decide that a backwash or back pulse is needed. So back pulse is needed. Okay, so you do the back pulse and then and then restart the membrane. But remember, this value or the so-called clean membrane value is now greater than your virgin membrane value. Okay, so as the time will progress, you will see that the so-called clean membrane value is increasing, and and at some point of time your fouled membrane resistance or transmembrane pressure is touching your maximum allowable pressure. So at this point you understand that the next cycle when we run, the cycle length will be lower and will not be able to, our membrane will not be, serviceable any longer. So at this point of time, you try to do what is called a chemical cleaning. So chemical cleaning is nothing like, you will talk about how the chemical cleaning is done. So you use some kind of a detergent, so that the hydrophobic bond between the particle and the membrane. So the membranes are hydrophobic in nature. I will discuss it very quickly, as soon as possible. But so you use detergents to do it, and you use pH, and all this variation should be there, so that you can do the chemical cleaning. And after you do the chemical cleaning, it is expected that you reach the same level here. So, and then you start from here again, you reach here, and you do the chemical cleaning, and this is how the system will go on. But even after chemical cleaning, you are not guaranteed that you will be getting the same thing as the thing or new membrane. So there are different types of resistances in the membranes developed during the cross passage of time. So let us do some calculations here, and then try to understand the thing. So let us say we have an MF membrane. So we have an MF membrane, and which is clean and new. Okay, and we pass deionized water through the membrane, and the flux was 850 liter per meter square at 20 degrees centigrade and 0.9 bar. Okay, so calculate the membrane resistance coefficient. So how would you do this? Fine. So we know this formula, J equals to delta P divided by mu into Km. Okay. Okay. And so we will plug in the values and try to find out. So we want to find out the value of Km, because resistance coefficient. So that means you have delta P divided by mu times J. Okay. So let us take mu as 1 into 10 to the minus 3 kg meter per second. Okay, kg per meter per second, and write the numbers. So we have 0.9 bar. So 0.9 bar means 0.9 1 bar equals to 100 kilopascal, right? And it is so 1 kilopascal, so that means 10 to the 5 pascal, or this is equals to 10 to the 5 Newton per meter square, which is equals to 10 to the 5 kg per meter second square, right? So 0.9 bar, right? So we'll write 10 to the 5 kg per meter second square. And then we can keep it in second also, but let us you know, normalize it because it is liter and this is meter square. And so we and this is, sorry, we have liter per meter square hour. Okay, so this is the value. Okay, so here we have meter square per hour. So let us convert everything into hour. So we have 3600 seconds per hour. Okay, and we have 10 to the 3 liter per meter cube, because नीचे से वो है ना, you have J is in different unit. Okay, so mu equals to 1.010 minus 3 kg per meter second, and we have 850 liter per meter square hour. Okay, and for this we have this factor for liter conversion. So if you calculate this, I have done this, so it is coming to be equals to 3.81 times 10 to the minus 11 per liter. So this is the membrane resistance coefficient for this membrane. Okay, now this membrane coefficient is, we have also, you can say that flux to the membrane will also be dependent on the value of mu. Okay, because mu is going to change. Km is an intrinsic value for a particular membrane. Km is an intrinsic value which is not going to change, for any environmental change in the temperature. So how we can so the way we have for different operations, so you can see that mu varies with temperature. So mu is temperature dependent. For a particular fluid, mu is temperature dependent. So if the mu is temperature dependent, then obviously J will be changing, depending on the temperature. So we can write this as, so if Js is like at standard temperature, and then we can write that standard is like 20 degrees centigrade, or let me write this as J as in 20. The same way we defined our DOD equations, we can write J at any particular temperature M. We can write this as 1.03 to the power T S, or sorry, 20. Okay, so where we have Tm is the temperature at which we require this. Okay, all right, and sometimes we also specify this flux as a at a standard temperature divided. So we also have a term called specific flux. So JSP is specific flux, and that is defined to be equal to J at any temperature. So let's say 20 degrees centigrade temperature over delta T. Okay. So if we have this specific flux value, then we can have comparison between different membranes. Then we can say key what are the specific values for the fluxes. Okay, so we can normalize the flux to account for temperature and pressure variations, and the effect of fouling also can be determined. So let us also try to do a small calculation here concerning the specific flux. Um, okay, all right. So we have a membrane. So there is a membrane, right? MF membrane. Okay. Flux values were measured. So one value was measured in March, okay, and the value was 80 liter per meter square hour, okay, at 0.67 bar, okay, and temperature was 7 degrees centigrade, okay, and in July the same membrane flux was measured and it gave us 80 liter per meter square hour at 0.52 bar pressure at a temperature of, let's say, 27 degrees centigrade. Okay, so the question is there a change in the specific flux value? Okay, and draw inferences from the result. Okay, so let us try to find out that the membrane, what will be the flux in, this is 80 liter per meter square hour at 0.67 bar at 7 degrees centigrade. Let us convert it into 20 degrees centigrade. So J20 equals to your Jm into 1.03 into 20 minus, we have 7. Okay, so like at 20 degrees centigrade, what would have been the flux for this membrane? Okay, so we can write this is 80 liter meter square hour and 1.03 20 minus 7. Okay, and that gives me close to 117 liter per meter square. So that means for the space for this membrane, if it were operated at this condition, at 20 degrees centigrade, this would have produced a flux of 117 liter per meter square per hour. So if we write the specific flux in this case, write JSP1, okay, in this case, we write that this is Js divided by delta P. This is standard temperature is 20 degrees centigrade. So we write, or you can write this as J20 divided by, okay. So in this case, we write this as 117 liter per meter square hour divided by 0.67 bar. Okay, so that gives me equals to 175 liter per meter square hour per bar. Okay, so this is the specific flux. Now, what will be the specific flux? What will be the J20? So this is in Feb. So sorry, March. Okay. So what happens in July? Okay, in July, again calculate J20, but here this is 27 degrees centigrade. Okay, so we write Jm is like 27 into 1.03, 20 minus 27. Okay, and this value is 85. So write 85 liter per meter square hour, and we have 1.03 to the power minus 7. So can you please calculate it for me?
So 69.
So this is 69 liter per meter square hour. Okay, and can we calculate the specific flux for this case is J20. Let us write this is 2. Okay, so J220 divided by delta P is what? 0.52. So delta P is equal to 0.52. So sorry, you can make it 0.62. You make it 0.62. So what is the value that we are getting?
111.29.
111. So we are getting 111.2 liter per meter square hour per meter. All right. So this was the performance, in both the cases. Now we can see there has been a deterioration in percentage. There is a deterioration in performance because the same membrane, the specific flux or per unit, pressure, the flux would have been the same, but this is showing, difference here. So it is 175 here, and now it is showing 111. So something has happened, but let us calculate what is the percentage loss in performance. Is nothing but 175 minus 111.2 divided by 175. So this is the percentage loss here. Okay, I mean multiply with 100. To get the percentage. So what is the percentage, tell me? And
36.
36%. So that means, we have a loss in, although my plant is giving, 85 liter at, higher flux at a lower pressure, so it is giving me higher flux at a lower pressure. So normally what we would have thought that, well, if it is so, then my membrane performance is better. But this is not, because the temperatures are different, and your actually membrane would have given better performance, but you have a loss in performance. And what is the loss in performance due to? So drawing inferences from this result is that seemingly, the specific, flux value has declined from 175 to 112, 111 value. Okay, so seemingly the membrane, although it seems to operate at a lower pressure during half flux in July, but there has been a loss of performance of 36%, due to loss in performance. What might be the cause of loss in performance? Yes, loss in performance due to fouling, because your membrane has got fouled. That is why the performance is lower. And how to how to make this performance better? Probably all these membranes you are, this may be due to your internal, fouling, or maybe due to formation of cake layers on the membrane. So there has been now, as we said, the fouling can have like three ways.
रुक जा 2 मिनट बचे बंद कर दे
मैया रे
कितना
306
Is that
चल जो
अरे 2 मिनट बचे 2 मिनट में गड़बड़ हो जाएगी देख ले 11 ठान बस 11 ठान बंद कर दी
दूध का कनेक्ट कीने हां
दूध कनेक्ट होंगे तो दूध में कनेक्ट किए हम 10 कनेक्ट किए
तीन कनेक्ट हां
तो चाची इनके कनेक्ट हुए
वो को हां सब चुप
ये मैं इतना 200 MB लागू कर दूं
let us now discuss fouling of the membrane.
50% से मैं कर दे जाएगा कई बजे हो रहा
Very
क्या कर रहा है 50% के
अरे बहुत एयरटेल का डाटा बहुत जल्दी होता है स्पीड बढ़ जाता
So there are two ways that this can happen. One is pore blocking. Simply you have pores here on the membrane. See, these are the membrane material.
थोड़ी देर पहले आया और
So suppose
10 मिनट पहले हाय बताइए 1 मिनट में कितना खर्च है
and what we can do there. Suppose there is a particle 6 levels, okay? And it blocks the pore so that the water cannot pass through. So this kind of blocking is called pore blocking of the particles. Okay? So particles blocking the pores. Particles blocking pores is one phenomenon. Okay, and there will be another phenomenon as constriction of pore, constrictions of pore. So where we not actually block the pores, but we have suppose this is your membrane. Okay. Suppose this is your membrane surface, and what happens that water also passes through the pores. So the pores, the water passes through the pores. Now, if there are tiny particles that actually develops on the membrane surface, sometimes the pores can be plugged. So we have pores are plugged. Okay? And this is called constriction of the pores, because the passage or
अरे इनका बंद कर रहा है
that was earlier,
बंद कर रहे हैं
they get constricted by the revolution of the particle. So this is one way that can happen. And third is
और इसको
cake formation.
हां
तो एक बचा
कितना
बस खत्म करना पड़े वाला अगली क्लास नहीं होगी बात
Cake formation is nothing but the formation of particles, and on top of this.
हमें देखे ले आप कितना डाटा
Okay.
कितना डाटा
And on
मतलब
top of
कितना
this,
डाटा लाग है?
there is some-
सिंपल तरीका कि को कितना यूज की
358
So this is your memory.
इंडिविजुअल में बता दे यार
Keep there.
कोई जरूरत नहीं है दिखा
Restrict the flow of water.
हाँ?
Okay. All right. So let me stop here today, and we'll discuss
चल जा हम आज में
more discussion on this. Okay. I have another class already. The time is over. Our class one. So okay. Thank you for being with me.
रुक जा अटेंडेंस भाई ये यार हो तो लास्ट के सफर में आ गई
Okay. Thanks for being with me, and I will see you one month.
बोले पर प्रोजेक्ट सर
डाउनलोड हो जाते हैं ऑनलाइन बोलो
लाल
हाँ चाचा बाजार में है हंसिया पिटावत हैं हंसिया पिटावत हैं हाँ खाना का पूछा था कि भैंसी धोआ का बंद कर दे बाबा बंद कर
ये थोड़ी देर बाद 90% क्या मैसेज
अरे 100% क्या है